So we finally get to a very simple but important characterization of a mixed Nash equilibrium, which is widely used, and that is that for a finite game, it's important that it's a finite game. For an infinite game, it should be a bit changed. For a finite game, a profile is a mixed Nash equilibrium if and only for each player, for every player, every pure strategy in the support on that player's strategy is a best response. So it's not only it's that every strategy is a best response to what others do. So P star I has to be a best response to the P star of minus I. That is by definition of a Nash equilibrium. But P star is a mixed Nash equilibrium. We state, we claim, if and only if every pure strategy in the support of P star I is a best response itself. So the proof is simple, but it has a lot of notation, unfortunately. So assume that in one direction you have an Nash equilibrium P star, and assume to the contrary that you have I in the support of P star I, which is not a best response to P star minus I. Then take any Ti, which is a pure strategy, which is a best response, and now we basically move the weight from Si, which we assume is not a best response, and it's in support, so it has a positive weight, and we move its weight to Ti, and we should get contradictory, of course, something better than P star I. So formally we say define a mixed strategy Pi instead of P star I in the way that it's defined as P star I for every, in the sense that the weights of all these pure strategies besides Si and Ti are the same. Now the weight of Si is now 0 instead of something positive, and the way of Ti is the previous way of Ti plus what was in Si, which was positive because Si, we assume it's in support. And it will give a strictly better result for I than Pi star, contradictory to the assumption that P star is in Nash equilibrium in the mixed extension. So assuming that P star is Nash equilibrium, we prove that everything in support of Pi, for each I, everything in support of Pi has to be a best response. In the other direction, however, now in the other direction, assume that for every player, J, every strategy in the support of P star J is a best response to the strategies of the other players, P star minus J. But assume to the contrary that there is a player which in general in this P does not optimize, that assume to the contrary that P star is not a Nash equilibrium, which means that there is a player I such that it can deviate to Pi and that will strictly benefit it relatively to P star I. Now then, the linearity of capital Ui implies that there exists a strategy Si in the support of Pi, the strategy to which player I has deviated, and a strategy Si prime in the support of the original strategy of player I in P star, such that S star gives a strictly better result for player I against P star minus I than S star I. And that implies that actually S star I was not in the best response of I to P star P star minus I, and that contradicts our assumption that every strategy in the support of P star any player is a best response. So it's a bit of a plane without definitions, and now we have proven that the Nash equilibrium of a mixed extension is characterized by every strategy and support being a best response. And a corollary from that is that given any mixed Nash equilibrium, so any Nash equilibrium of a mixed extension, for each player, every strategy in the support of that player in that mixed Nash equilibrium yields player the same utility. Because as we just saw, there has to be a best response. In particular, it yields player the same utility. So to wrap up, summing what we have done, we have given a sufficient existence result for infinite games. I'm saying infinite because we required convexity, which means that if there is at least two strategies, then demanding that everything between them will be also a strategy implies that the number of strategies is infinite. Actually, it's even continuum, not only that it's infinite, it's even uncountably infinite. And then we said, yeah, but what about finite games? But for those games, we say that in that case, at least we know that for the mixed extension, there exists a Nash equilibrium in the mixed extension. So in any game, we can define a mixed extension, but we've proven that if the game was finite, then the mixed extension always has at least one Nash equilibrium. You're welcome to mail me your questions.